Watch a modern image model work and you see the same magic every time. It starts with pure static, the gray fuzz of an untuned television, and a few seconds later there is a face. A real, plausible, never-before-seen face. Everyone explains this with one word. It denoises. It cleans up the static. That word is true, but it is also where almost every explanation quietly stops, right before the interesting part. Because here is the question nobody answers. Why does nudging static toward a face about 30 separate times produce something coherent, when nudging it once does not? And stranger still, why do the newest models pull it off in only 4 nudges, or sometimes a single one? If it were really just cleaning up a photo, you would do that in one pass. 30 passes, then 4, then 1, is not what cleanup looks like. It is what something else looks like. The honest answer is one genuinely beautiful idea, and once you see it, every generator in this whole season clicks into place at once. The model is not cleaning a picture. It is following a set of arrows downhill, out of an empty void, onto the thin surface where real things live. Let me show you those arrows. First, let us kill the most common wrong picture because it blocks everything else. A generator is not a clever search engine. It is not stitching together bits of photos it has memorized, not a collage, not a lookup. What it is actually doing has a precise name, and the name is the whole secret. It is sampling from a distribution. Picture every possible image of a certain size as a single point in an unimaginably large space. A modest photo is a point in roughly 3 million dimensions, one number per color per pixel. Almost every point in that space is meaningless static. Only a vanishingly thin sliver of it looks like anything real, a face, a street, a cat. Mathematicians call that thin sliver a manifold, a curved surface where the real data lives, floating inside an ocean of garbage. So the task is brutally simple to state. Land on that surface. Produce a fresh point that the real world would have found plausible, one that has never existed but easily could. Not retrieved, not copied, sampled. Everything else today is about how you possibly find that razor-thin surface when it is lost in 3 million dimensions of noise. So how do you find a surface you cannot see, starting from a random point in the dark? You do not need a map of the whole space. You only need one humble thing at every location. A single arrow that says, from right here, which way is more real. Stand anywhere in the void, and the arrow points slightly toward the nearest part of that data surface. Cover the entire space with these arrows and you get a field, like iron filings around a magnet, all gently leaning toward where real things live. That field has a technical name, the score, but you can just call it the more real direction. And here is the part worth slowing down for because it unifies half of this field. You will hear 3 different words for what the model predicts. Some models predict the noise to remove. Some predict the clean image directly. The newest predict a velocity, a direction to move. People argue about these as if they were rival approaches. They are not. They are 3 names for the same arrow, written in 3 coordinate systems. Noise, score, velocity. 1 arrow, 3 names. Predict any one and the other 2 follow by simple arithmetic. The only reason a model picks one over another is which is steadiest to learn from. Predicting the noise gets shaky near a clean image. Predicting the clean image gets shaky near pure static. And the velocity is the blend that behaves well from end to end, which is why the newest models predict it. The model, underneath all the jargon, is learning that single field of more real arrows. Now here is the subtle problem that defeated the first attempts, and the elegant fix that makes the whole thing work. Suppose you have this field of arrows and you just drop a dot into the void and let it follow them. It should glide to the surface. But it does not, and the reason is sneaky. The arrows are only trustworthy near where real data actually is, because that is the only place the model ever saw examples to learn from. Out in the vast empty middle where you are forced to start, the model has essentially never been. Its arrows there are guesses, garbage, pointing nowhere useful. So the dot wanders, lost from its very first step. The fix is the heart of it. Do not train the model on clean data and one tiny bit of noise. Train it on the data blurred to many different levels, from a faint haze all the way up to total static. Total static fills that empty middle with examples, so now the model has seen the void and can give a sensible arrow even there. Then you sample in stages. Start from pure noise, follow the arrows for the heavily blurred world, which are coarse but at least point the right way. As the dot gets closer, switch to the arrows for sharper and sharper worlds. You are walking the dot down a ramp of decreasing noise, handing it off from a blurry guide to a precise one. That staged walk, many noise levels instead of one, is exactly why a generator takes many steps and not a single leap. Now I owe you the deepest reason any of this is hard, and it is the single most counterintuitive fact in the field. It will feel wrong, and it is true. Your instinct says if you want a typical sample, head for the most likely point, the peak, the center of the blob. In 1 or 2 dimensions, that instinct is correct. In high dimensions, it is catastrophically wrong. Take a simple bell-shaped cloud, but in 100 dimensions. Where do its samples actually land? Almost none of them land near the center, the very point with the highest probability. Instead, they pile up on a thin shell, a hollow sphere, far out from the middle. Picture a soap bubble. All the soap is in the thin skin. The whole inside is empty, even though the exact center is the single most probable spot. How can the most likely point be the emptiest? Because as you move outward, the probability of any one point drops, yes, but the amount of room out there, the sheer volume of the shell, explodes far faster. Volume wins. So the real, typical samples live out on the skin, and the bright peak in the middle is a place almost nothing ever visits. This is the deep punchline. The most likely point is not a typical sample. If you greedily chase maximum probability, you walk straight off the surface of real things and into a dead zone, and you get nonsense. Older audio systems did exactly this and produced pure silence, the single most probable but utterly atypical sound. This is the real reason you cannot just leap to the most probable image. You have to take a guided walk that lands you out on the living shell where real data actually breathes. So the model gives you a field of arrows, and you know you have to walk, not leap, to land on that living shell. The thing that actually does the walking has a name too, and it is humbler than it sounds. It is called a solver. A solver is just a recipe for taking steps along the arrows. Read the arrow here, step a little that way, read the new arrow, step again. That is it. And this is where those step counts from the start come from, because the recipe is a knob you turn at the end, without retraining the model at all. There are 2 flavors worth knowing, and they answer 2 different questions. The first flavor walks in a perfectly smooth, deterministic line. Same starting noise, same final image, every single time, no randomness on the way. The classic version of this is called DDIM, and it is the one that lets you take big confident strides, 50 steps instead of 1,000 because the path is clean. The second flavor, the ancestral or DDPM style sampler, adds a little fresh random jitter at each step, a controlled wobble. It is messier, but that wobble can shake the dot loose from bad spots and explore more variety. Here is the elegant part. Both flavors are walking to the same destination, the same shell of real images. They just take different routes there. So choosing a solver is not changing what the model knows. It is only choosing how carefully and how randomly to walk the path it already laid down. Faster, smoother, more varied, all dials on the same trained field. And the smooth, deterministic walk hands you a bonus that turns out to matter enormously later. Because there is no randomness in it, the path runs cleanly in reverse. Take a finished image, and you can walk that deterministic route backwards to recover the exact patch of noise that would produce it. The noise-to-image map becomes a 2-way street, an invertible one. Hold on to that, because finding the noise behind a real photo is the hidden key to editing a real photo, which is a whole episode of its own. Which brings us back to the headline mystery. Why can the newest models do in 4 steps or 1, what used to take 50? 2 clean ideas, and neither is magic. The first is straightening the path. If the route from noise to image is a winding curve, you need many small steps to follow it without flying off. But what if you could iron that curve into a straight line? On a straight line, you can take one enormous stride and land exactly right. There is a training trick called rectified flow that does roughly this. You let the model lay down its winding paths, then retrain it on its own start and end points, which lets it draw straighter routes between them, and you repeat. Each round the paths get straighter, and straighter paths mean fewer steps. This is why the current generation of image models defaults to flow-style training. The second idea is even bolder: distillation, and it comes in a few flavors worth knowing by name. Take a slow, excellent model that walks the full 50 steps, and train a fast student model whose only job is to memorize where each starting point ends up. The student does not learn to walk the path. It learns the destination, so it can teleport straight there in one jump. Walk versus teleport. The cleanest way to picture how the boldest version, the consistency model, can possibly work is this. Every single point along one of the teacher's winding paths is secretly heading to the exact same final image. So you train the student on one iron rule. No matter where on a path I drop you, point at that one shared endpoint. That property is called self-consistency, and it is the whole trick, because once every point on the path agrees on the destination, the student can leap from the very first point straight to the answer. A gentler cousin, progressive distillation, gets there by repeated having instead. Train a student so that one of its steps does the work of 2 teacher steps, then distill that student again and again, each round having the step count 50 to 25 to 12 and on down toward a handful. Now the honest caveat, because there is no free lunch here. A single teleport step usually looks a little worse than the careful 50-step walk, slightly less sharp, slightly less varied. That is why most products in practice settle around 4 to 8 steps, the sweet spot between instant and excellent, not a true single step. And the frontier is moving fast. There is recent work that learns genuine one-step generation from scratch, with no slow teacher to copy at all. Striking, real, but still early, and not yet the standard. Treat every step count and speed claim you hear as a snapshot that will change by next year. Let me clear up a confusion that trips up almost everyone reading about this because the headlines make it sound like a war. You will see 2 camps named diffusion and the newer flow matching or rectified flow. The press loves to frame it as flow matching beating diffusion, the new thing killing the old thing. That framing is wrong, and seeing why is genuinely clarifying. They are not rivals. They are the same idea in different clothes. Both build a path from noise to data and train a model to move along it. Diffusion happens to use a particular curved, bell-shaped noising schedule. Flow matching uses a simpler, straighter one. That is very nearly the whole difference. In fact, here is the precise statement worth keeping. Diffusion, run with the smooth, deterministic solver we just met, is exactly the special case of flow matching where the path is the bell-shaped one. One is a member of the other's family, not its enemy. The reason flow matching feels newer and better is mostly that its straighter paths need fewer steps, which is a real practical win. But it is a cleaner rederivation and a better default route, not a different physics. So when you read that some 2026 model uses flow matching and another uses diffusion, hear it correctly. They are cousins doing the same thing, following a learned field from noise to the data shell, just along differently shaped roads. One piece is still missing, and it is the one you actually care about as a user. So far the dot just walks to some real image, but you typed a prompt. You did not ask for a real image, you asked for an astronaut riding a horse. How does a word steer the arrows? The trick is clever and a little sneaky, and it is in nearly every diffusion model you use. You run the model twice at each step. Once told the prompt, astronaut on a horse. Once told nothing at all, just make any real image. Now you have 2 arrows from the same spot. One points toward, roughly, all real images. The other points toward real images that match the prompt. Subtract them and you get a pure direction, the part that is specifically about the prompt, the difference between generic and astronaut. Then, and here is the move, you do not just follow that prompt arrow. You exaggerate it. You push harder in the prompt direction and harder away from generic than the model alone would. That is the guidance knob. Turn it up and the image obeys the prompt more sharply. But predictably, there is a cost, and it ties right back to our soap bubble. Push too hard and you shove the dot off the natural shell into an extreme, oversaturated, almost garish region, vivid colors, blown-out contrast, sometimes mangled details. Too little guidance and the image ignores your words. Too much and it stops looking real. And it is not free, because running the model twice on every step roughly doubles the cost, which is why recent work tries to get the same steering for less, applying it only on the middle stretch of the walk, or training it away entirely. So guidance is a balance, a hack that works beautifully in the middle and breaks at the edges. It is not a solved, optimal thing, just a remarkably effective steering wheel that the whole field still tinkers with. Before we close, the honesty this whole season runs on, because the cleanest version of this story is a little too clean. I told you the model learns a field of arrows pointing toward the true distribution of real data. Here is the uncomfortable open question at the center of the field, right now. If a model learned that field absolutely perfectly, it would point only at the exact training images it was shown, and nothing else. A perfect score would just memorize. It would spit back the photos it studied, not invent new ones. But real models clearly do invent new ones, faces and scenes that were never in the data. So the truth must be that they learn a slightly blurred, smoothed, imperfect version of the field, and somehow that very imperfection is what lets them generalize instead of photocopy. And here is the genuinely honest part. Exactly why, and even whether, they generalize rather than memorize is still openly unresolved research in 2026. People are publishing on it right now. So when someone tells you a diffusion model learns the exact gradient of the data, gently correct them. It learns a smoothed approximation, and that smoothing is doing quiet, not fully understood work. Two more honest edges. The labs making the images and video and voices you use mostly do not publish their exact recipes. So any confident claim about what is inside a closed model is an educated guess, not a fact. And one step is still not truly free. But none of that dents the core idea, which is now yours. A generator does not search or stitch. It learns a field of more real arrows and walks a dot down a ramp of noise, out of an empty void, onto the thin living shell where real things actually are. 30 steps, 4 steps, 1 step. Diffusion, flow matching, guidance, distillation. Every one of them is a different way to follow the arrows downhill. That is the engine. The rest of this season is just watching it paint, move, speak, and build worlds.